All right, so first talk this afternoon of the meeting is by Dan Grayson, and he's going to talk on computations in intersection theory. Thank you.
Okay, thank you. First of all,
could you go back on?
You writing down my title? Oh, the archive number. Yeah, there's the archive number of the paper. My co-authors, I should have said, are Alexandru Seceleianu, who used to be at the University of Illinois with me, and Michael Stillman, who's at Cornell. Can't hear. Oh, is the microphone on? I'm under the impression it is. Testing, 1, 2, 3. What?
4, 5, 6.
So, it's certainly on. A point of arithmetic. I've been friends with Steve for 39.9 years. I became his doctoral student 39.4 years ago.
Do you count the friendship from when you first arrived at MIT or after 3 months?
Oh, I don't know. I think it was friendship at first sight.
Only one decimal digit. Then, why only one decimal digit?
Well, actually, I couldn't remember the exact day. So anyway, this talk is about algorithms that are used in software for computations in intersection theory. The first one is the Maple package Schubert, which was written by Stein-Arlt Ströme and Sheldon Katz about 20 years ago. And the second one is the Macaulay 2 package Schubert 2, written by me and Stillman, Eisenbud, Ströme, and also Charlie Chrisman, a postdoc at Berkeley. The Maple package no longer runs under the current version of Maple. The last version of Maple it ran under was Maple 8. And both packages depend on the same sort of assumptions about the intersection rings of the varieties that are used. These varieties are flag bundles. And these assumptions are natural and have worked out numerically, but it seems time to justify it. And the justification involves taking a look at Grobner bases, and they turn out to have a very beautiful explicit form, which you'll see. So first of all, we start with flag bundles. That's part one. Part two will be isotropic flag bundles, and then that'll be the end. So let's let X be a non-singular variety. Let's let A of X be the intersection ring of X. Let's let E be a vector bundle on X of rank N, and then pick some numbers, N1 up through NR. And then we introduce the flag bundle of E over X associated to this list of numbers. It's the scheme over X that parameterizes filtrations of E, pulled back to whatever test scheme you have in mind, where the steps in the filtration have the specified ranks, N sub I, that are listed there. And I'd like to draw attention to the fact that I don't list all of the ranks. There's, oops, wrong button. This final inclusion here is not an equality, as it might ordinarily have been. And that way, I don't mention anywhere the rank of E0. It's not specified to be the rank of, to be the number N0. But of course, you could deduce it by subtracting the sum of the N sub i's from the rank of E. So it's a trivial modification, which just seems convenient for the notation. So for example, if you take just R equal 1 and N1 equal to 1, then you get the projective bundle of E. So then we introduce the Chern classes, but instead of taking the total Chern class, I make a polynomial out of it in this way in a new variable X. A monic polynomial in that variable. And then the main point about this flag bundle is that when you pull E back to the flag bundle, it has that filtration. And the main point about Chern classes is multiplicativity along short exact sequences and thus along filtrations. And so we get this formula for pi upper star of the Chern class of E as a product. And then the Chern class of E sub 0, I'm going to not pay attention to since it can be deduced from the other ones by dividing. So let's just state that pi upper star is divisible by the product of the other ones. And we'll focus on examining that situation. Now I introduce some notation. Given two polynomials, f% g will be the remainder of f upon division by g, if g is monic, and f triple equal sign g will be the ideal of A generated by the coefficients of f minus g. And thus, f% g triple equals 0, that's going to be the smallest ideal of A modulo which f is divisible by g. So now we introduce the concept of universal factorization. Let's start with some elements of A and take a general monic polynomial f of degree n. This is supposed to be a model for the Chern class of E on the previous slide. And then let's take the same list of numbers, n1 up through nr, and let's consider a new polynomial ring over A where we adjoin a whole bunch of variables that are going to serve as coefficients of a whole bunch of factors. The number of factors is going to be r. And those are supposed to mimic the Chern classes of the successive quotients in the filtration on the previous slide. And so we introduce gi, a monic polynomial of degree ni, and then we take the ideal that is the smallest ideal that ensures that f is divisible by the product g1 up through gr, so that simulates a relation that we know is true in the intersection ring in the flag bundle. But this is this ring, R mod I, then is the universal ring that supports divisibility of f by a product of R factors, monic of those degrees. And so we give it a name at this point, this, oops, wrong button. It's this PF sub n1 up through nr of f. It's the universal ring supporting R, a divisibility of f by a product of R such factors. And then it can be made into a graded ring if A happens to be graded, with the degree of bi being I, take degree of x to be 1 and take the degree of Cij to be j. Stop me if there are any questions. So the main theorem about intersection rings of Grothendieck from 1959 is that the map from this universal factorization ring to the intersection ring of the flag bundle is an isomorphism. And the map is defined by sending the coefficient to the appropriate Chern class, which is what you expected from my presentation. So now we introduce Gröbner bases as a computational tool. What are we going to apply it to? We're going to apply it to the intersection ring by interpreting the intersection ring as this universal factorization ring. And that's a polynomial ring modulo I. So we're going to be, to compute in the intersection ring, we're going to be examining the Gröbner basis of this ideal I. Gröbner bases are ways of computing in quotient rings.
Show the previous
What?
slide. The previous slide.
Even before this one?
Yeah, definition. Yeah.
Yeah. Back to this definition. The percent sign is the remainder if G is monic. I say G should be monic because I don't assume A is a field. Oh, you're photographing the slide?
Oh, I just wanted to remember.
Oh, all right. Yeah, it's too bad we don't have multiple screens and so on. All right, so that's the strategy. Grosvenor basis, the Grosvenor basis of that ideal is a computational 2 in the intersection ring. And so now I say what Grosvenor bases are. So if you've heard a presentation of Grosvenor bases, it was probably over a field. This is a presentation that works over any ring. Has to, since we started with almost any ring, the intersection ring of X. So A is a ring, and we take a polynomial ring, and in M variables, let's say, and we think of the monoid of monomials, give it this notation with the bracket X, and equip it with a monomial ordering, which means it's an ordering that makes this set of monomials well ordered and compatible with multiplication. So 1 will be the first, the smallest monomial, and then one of the variables is going to be the second smallest monomial, and then so on. So then we introduce notation for the lead coefficient of a polynomial, the lead term of a polynomial, and the lead terms of a set of polynomials for a subset of the ring R. And we say that a finite subset G of an ideal I is a Grosvenor basis of I if its lead terms generate the ideal of lead terms, the ideal generated by the lead terms of I. And then it necessarily generates I. That's a proof that uses the well ordering. And it's called a Grosvenor basis if, independent of an ideal I, if it's a Grosvenor basis of the ideal that it generates. And we say that a polynomial is monic if its lead coefficient is 1. That generalizes the notion of monic to polynomials in several variables. Since we're working over an arbitrary ring, and we're going to be dividing the usual way, we can't have coefficients other than 1 on our lead terms. So monic Grosvenor basis is a Grosvenor basis that consists of monic polynomials. And then since their lead terms are monomials, and they generate that ideal of lead terms of I, then that ideal turns out to be a monomial ideal. So then reduction of a polynomial modulo a set of monic polynomials is the algorithm that goes like this. You look for a monomial in F, say x to the alpha plus beta, which can be written in the form x to the alpha plus beta, where x to the beta is the lead term of some element of G. And you write that element of G as x to the beta minus h, and you rewrite the monomial x to the alpha plus beta as x to the alpha times x to the beta, and then replace x to the beta times h, which doesn't change the coset of I that you're in because x to the beta minus h is in I. That's the reduction algorithm. And then if G is a Grosvenor basis of I, then reduction modulo G puts F into normal form. So it's a computationally useful tool. And it stops when there's no more work to do. I think I should have said that. Well, I did say that, as long as possible. So think of it stopping. When it stops, there's no more work to do. So there are no more monomials divisible by lead terms of G. So none of the monomials in the polynomial that you're holding are in the ideal generated by the lead terms of I, because that's generated by the lead terms of G, according to the definition that we gave on the previous screen of what a Grosvenor basis is. The normal form depends only on the monomial ordering, on I, and on the congruence class of F. And then since we have this normal form that writes any element in the quotient ring as a linear combination of monomials not in that monomial ideal, if you call those monomials standard and take the set of them, then that gives you a basis for R mod I as a free A module. And as a corollary, you see that R mod A is a free A module if it has a monic Grosvenor basis like this, a Grosvenor basis consisting of monic polynomials. So then here's the theorem. Let R mod I be this universal factorization ring for a polynomial f that we described above. It's that ring that supports divisors a product of divisors G1 up through GR of F. And then equip the degrees, give the variables the degrees I said before, and equip each monoid consisting of the variables in block I with what's called the graded reverse lexicographic ordering. I'll tell you what that is. Where you order the variables themselves in descending order, and then you equip the monoid C of the polynomial ring. What was C? It was sort of implicit back here. This C was shorthand notation for the entire monoid of polynomials in this polynomial ring. So equip the entire monoid of monomials in that polynomial ring with the block lexicographic ordering. So block lexicographic ordering means that you look at batch 1 of variables, and you have a monomial ordering involving it, and you examine that monomial ordering on your 2 monomials of R first. And if it judges an inequality, you use it, and if it doesn't, if the leading part of your 2 monomials are equal, then you move on to the next one. And then the statement is that I has a Monnet-Grubner basis, and the lead terms of I, the lead term ideal of I is the ideal that's written there. It's a certain batch of variables, the first batch of variables to a certain power, second batch of variables to a certain other power, and so on. So it's explicit, and that's what it is.
Excuse me. So this means that you take, in each of these rows, you take monomials in those variables of that degree.
Yep. Except I'm going to restrain myself from calling it the degree, because those variables also have a degree.
Yes.
So one could say you take monomials on those variables where the sum of the exponents is greater than or equal to that number there. I think on the left-hand side it should say the ideal generated by the lead terms of I. So as a corollary, we see that the standard monomials provide a basis of this intersection ring as a free module over A of x. And that's reminiscent of the projective bundle theorem that gives a basis of, in the case where you have a projective bundle. And it also is proved in Fulton's book. It's called the basis theorem there. But the proof there involves Schubert cells and John Belli's formula. And now in intersection theory, you're interested in computing intersection numbers. So you're interested in pushing forward to the intersection ring of your ground field. And if you have a construction involving flag bundles that are constructed iteratively, starting from the ground field, then one way to do that is to just go back down the chain of flag bundle structure maps and apply pi lower star. So computing pi lower star is the relevant thing for learning how to get intersection numbers out. And it turns out that once you have this Grubner basis in hand, and once you can compute normal forms of elements in the intersection ring, then there's an easy way to pick out what pi lower star of any element is. So you just examine the list of monomials, examine the standard monomials from the theorem. And so I claim that this standard monomial here is the unique one of highest degree. So for example, if you look at C1N1, you should raise it to that power. Let's go back and look at the theorem. Standard means not in the lead term ideal. There's the power on the first batch of variables here is 1 higher. It's got that plus 1. So here we throw away that plus 1 to get something 1 less. And we do the same thing and take the product all along. And so this is, and the reason this is the thing of highest degree is because in the first batch of variables, C11 up through C1N1, the degree of the first one is 1 and the degree of the last one is N1. And so to get something of maximum degree, you take the last variable on the list. That's the one of degree N1. So that's the monomial of highest degree. And then the theorem is that pi lower star of the corresponding element of the intersection ring is equal to 1. And the corollary of that is that you can compute pi lower star in any element of the intersection ring by writing it in normal form and picking out that coefficient of that monomial. The top degree part of this intersection ring is rank 1 over the base. The normal form computes the coefficients of your putative element with respect to a basis, and you just take the coefficient. This corollary follows easily from the theorem. It should be immediate. Any questions about this point?
Why are you grading C2 into with grade 2? Why are you grading by names?
Pardon me?
Why are you introducing the different variables that really correspond? And why are you grading C2 into with grade 2?
The degree of C2 comma N2 is N2. It corresponds to the top Chern class of the second quotient bundle in the filtration. So the first subscript, of course, tells you which stage of the filtration you're looking at. The second subscript tells you which Chern class you're looking at. So the degree comes from the second subscript. The first subscript just tells which tautological subquotient bundle from the tautological filtration that you're looking at. The beta in the theorem is the same as the beta on the line above. It's sort of supposed to define beta for you. I should have mentioned that, sorry. I should have colored that beta in red.
So basically you're looking for the Z beta in that sum.
That's right. So beta is one of the alphas. It occurs in that sum. And you take the Z alpha where alpha is equal to beta. You take that coefficient.
Shouldn't you say that it's pi lower star of zeta?
Yeah. Which one's zeta?
Oh yeah, that's a misprint.
Oh, no, the last line.
Yes, it is the last line. In fact, there is no Z lying around for it to be. Yeah, so this pi lower star of Z is a misprint. It's pi lower star of zeta. Was that why you were staring so intensely? Oh. Oh, sorry about that. Okay. Thank you for staring intensely. It slides okay now, probably.
Yes.
Okay. So we're going to embark on the essence of the proof of the theorem. So let's first reduce to a special case by taking R equal to 1. That was the number of tautological vector bundles that we're considering. That was the number of divisors that we're considering. We'll just take R equal to 1. And so we equip it with the graded reverse Lex order, and then prove it in that case, and prove that the lead term ideal is generated as the n minus m plus first power of the ideal generated by the variables. And so here's the definition of graded reverse lexicographic order. It means that when you have two monomials, C alpha and C beta, then first you look at the degree. That's from the word graded. The degrees, if the first one is, we're defining what it means for C alpha to be greater than C beta. So first of all, that'll happen if the degree is greater than the degree of the other one. Or in case of a tie, then you look at the rightmost, you look at the rightmost exponent that changes. And if it goes up, then we have our monomials going down. So making a change to the exponents where the rightmost exponent changes, goes up, that makes the monomial go down. We'll come back to that. Now we have just one factor, so I simplify the notation from the general theorem by throwing away the first subscript. And now we just need the second subscript to be retained. And so there it is. It's just a repetition of what we had before. And now, instead of showing that the two ideals are equal, we're just going to show the containment. So we're going to try to locate some polynomials in this ideal whose lead terms can be identified as all of the monomials in C1 up through Cm with that number of factors. So now what we do is we remember that we're dividing f by g, and we model the division of f by g as elementary column operations on a matrix. We use the columns of the matrix to contain the coefficients of the polynomials. The first column has the coefficients of f. The rightmost column has the coefficients of g. The rows correspond to the powers of x, starting with x to the 0 at the bottom. And then we put g times various powers of x in the intermediate columns, as high as we need to go to start our Euclidean division algorithm going. And then the way division works is that we do column operations where we start by killing the 1 in the top of the first row with the 1 in the top of the second row. And then we use the 1 in the second row of the, sorry, did I say row? We use the 1 at the top of the second column to kill the 1 at the top of the first column. That puts a 0 at the top of the first column. And then we work on the thing that remains with the other ones. And after completing the division, we have the coefficients of the remainder remaining in the first column, a little bit lower down, below all of those ones. And now we use row operations in the upper part to produce many zeros. Let's go back to the matrix that we had before. Row operations kill everything below the ones. And they're killed. So now let's take a look at the ideal maximal minors of this matrix. There are a lot of ones, so it's generated by the d's, which are the coefficients of the remainder. So that's the coefficients of those remainder. Of that remainder, those are the ring elements that generate this ideal that would define I. So this is the ideal we're interested in. Now the row and column operations don't change the ideal of maximal minors. So the original matrix has the same ideal of maximal minors. It's I. And here's where we're going to find our Grobner basis elements. N minus m. So m is the degree of the divisor and n is the degree of f. And we have powers of the divisor, starting with x to the 0 times the divisor up through x to the n minus m times x to the n minus m times the divisor. So the number of columns to the right of the first is n minus m plus 1. The total number of columns is n minus m plus 2. That's what I say here. And now, from the form of the matrix, one sees that any monomial with the betas adding up to n minus m plus 1 occurs as a product of diagonal elements in a unique maximal submatrix that includes the first row. Let's go back and look at that matrix. Here's the way you do it. You write the variables in increasing order. Look at the first one, located in the second column. Use the row it's in. Then take the next variable, locate its variable in the third column. Keep going. So you find all of the monomials that way. For example, see if this particular monomial arises from the diagonal of this particular submatrix. So there it is. You can do that with any monomial, with that number of factors. Now we claim that that diagonal product is the lead term of the determinant of that submatrix. We're going to prove it. So we take a look at it, and we remark that we can make this, if the b's had, if the ith b sub I had degree I, then this matrix would have a determinant, every term of which had the same degree. But those bi's are scalars. They come from the coefficient ring, so they don't have degree I. They have degree 0, which is strictly less than I. So any term of the expansion of the determinant that involves one of the bi's is going to have degree too small in reality. So we can ignore them And the only terms that are going to be relevant are the terms that use the 1 in the upper left-hand corner, and then the remaining factors in the term are going to come from the lower right-hand block. So we discard the first row and column. And if we discard the first row and column from the original matrix, it would look this way. So we'll be looking at the maximal minors of this matrix. And if we do that to our minor, then we get this. Now we want to show the other terms of the determinant give smaller monomials. We remind ourselves what graded reverse lexicographic order is. First you look at the degree, and then you look at the rightmost exponent that changes, and if it went up, the monomials went down. We don't have to look at the degree, because if in this matrix, every single term of the determinant has the same degree. So all of the degree comparisons come up with equalities. So we're just going to be looking at what happens to the exponents. To test what I just said, try examining a 2x2 subminor and check that the degrees of the two terms in the determinant of 2x2 subminor are equal. So now consider some non-identity permutation that gives you a term of the determinant. For example, it might give you the product of the entries that are in boxes. So now pay attention to the right. Pay attention to the bottommost row where we take something off the diagonal. That's this row number 4. There, instead of taking C7, we took C8. And the idea is that changing C7 to C8 increases the exponent of C8 that we had. And that's the rightmost change that could possibly occur. The exponent of C7 conceivably decreased because we changed C7 to C8. The ones further up the diagonal, like C5, C5, and C4, their exponents could also decrease, but no other exponents could decrease. So the rightmost change involved an increase in the exponent, and so the monomials got smaller. So that shows the containment. And then equality is established by using computation of Hilbert series, showing you get equal ones, reducing to some simpler case over a field where you can use a dimension argument to conclude equality. So here are some examples. Let's do the Grassmannian of lines. N is 4, M is 2, F is x to the 4th. That big matrix looks like this. The one where you remove the first row and column looks like that. Take the determinants of the minors, and you get these things. And I've highlighted in red the leading terms of the various polynomials. These are all members of the Grubner basis. They form a Grubner basis. This is the Grubner basis of that ring. Think of reduction modulo the Grubner basis as applying the following rewriting rules. And let's compute the number of lines meeting 4 general lines in space. Right here. C1 is the class of the variety of lines meeting a given line. C2 is the class of the variety of lines lying in a plane. And C2 squared is the class of a point in the flag bundle, class of a single line. It's a special case of the formula I gave for a class whose pi lower star is equal to 1. So there's the computation. C1 to the 4th is divisible by C1 cubed. So replace that factor by 2 C1 C2. Then look at what you get. You've got C1 squared C2. There's a replacement above, so replace that by C2 squared. And C2 squared is class of a point. So you apply that algorithm, and you get 2. That's how the algorithm works. So here's an example from the code. Number of lines on a cubic surface. Take the flag bundle lines in 3 space. and then 27. These examples are drawn from Schubert's copious compendium of examples. The third symmetric power. So what does the code look like? The first line, we create the flag bundle. The 2 and the 2 are the ranks of the subquotient bundles that we want. Same as the notation that I gave earlier on, F sub 2 comma 2. And then this line 3, we do S comma Q equals something. We get the subbundle and the quotient bundle from the total logical filtration. And then Q is the quotient bundle. We take this third symmetric power. That's considering what happens when you take a cubic form and restrict it to one of those lines. And having it vanish is what's relevant. Here's the number of lines on a quintic threefold. It's the same sort of thing with different numbers plugged in. Here's the number of elliptic cubics on a sextic fourfold. This is an example of a construction where we do it twice. First we make a flag bundle, then we take a particular vector bundle on that and take the projective bundle of that flag bundle. So it's a two-stage construction. And you can actually figure out why the thing is supposed to give that answer if you examine the code with a bunch of thought at the bar tonight. And now part 2 of the talk, 7 minutes long, is about isotropic flag bundles. So start with a vector bundle of E of even rank on a non-singular variety and give it a non-singular alternating form. So by non-singularity, it's isomorphic to its dual, and that means the odd-numbered Chern classes are 2 torsion, but they actually vanish, as you can show by a lemma. And now we take the isotropic flag bundle, which I should have colored in red. It's similar to the flag bundle that we had before, except the flags involve reference to the form on E, which is sticks around when you pull it back to F. So the flags have this shape. The only part that's variable is the bottom half. And then what's on the top half consists of the orthogonal complements of what's on the bottom half. And so any one of those flag bundles in the bottom half, E sub I, is contained in its orthogonal. That means the form, when restricted, it vanishes. That's called a totally isotropic flag bundle. It's a totally isotropic subbundle. And so you get the flag that looks like this. This flag bundle parameterizes such filtrations with the ranks as specified, because the dual of the bundles of the quotient bundles in the bottom are isomorphic to the quotient bundles in the top by the non-singularity of the form. The ranks of everything else is specified, and you have a little bit left over between E0 and E0 perp, which is sort of analogous to my ignoring E0 in the previous definition of the flag bundle. And so by multiplicativity, you conclude that pi upper star of the Chern class of E is divisible by this product, where the C star is my notation for the expected Chern class of the dual bundle. So I've already rewritten, using this duality isomorphism in the middle, what the product of the Chern classes of all of the subquotients is, except for the subquotient right in the middle. So they come in pairs, one at the bottom, one at the top, and one of them is dualized. And what happens when you take the Chern class of a dual bundle is well known. I mimic it with these monic polynomials, G sub I and G sub I star here, by changing the signs of the odd-numbered coefficients. And then we do something similar. We take we model the intersection ring by the universal ring that supports such a product supports F being divisible by such a product. And we give that a name, it has a universal property. And then the theorem, our theorem is that the corresponding map to the intersection ring of isotropic flag bundle is an isomorphism. And we look at that ideal I, we introduce some notation. SQ denotes the operation on monomial ideals that squares all of the monomials in it. And the lead term ideal of this thing turns out to be SQ of something that looks really a lot like what we had before. So the surprise is that it turns out to be describable. The surprise is that when you choose the right monomial ordering on the ring, same one as before, and compute the Grubner basis in the computer, you see this pattern. You see what the lead terms are. And you see that the coefficients are all 1, and that's why you suspect this theorem is true. So the idea of the proof is that you write hi for the product gi times g star, and you look at one of its coefficients. The coefficient of x to the 2j is expanded there, and the lead term is in the middle. That's because on either side, you have an exponent of a later variable that got increased. On the right-hand side and on the left-hand side, both, the thing whose second subscript is j plus 1 had its exponent increased. And so those are smaller monomials. And if you apply the previous theorem and plug in this substitution and take the leading term of the result, then it has the effect of squaring everything. Just by a miracle. That's the miracle right there. The lead term is in the middle. The cross terms don't matter. Everything gets squared. So we identify a class, pi star of which is equal to 1. It's a standard monomial. It doesn't go away during the reduction to normal form. It survives. And we implement it in code. And here's an example where we compute the number of totally isotropic 5-planes meeting 15 in a 10-dimensional symplectic space with basically the same notation as before, except in this case, now we have 3 stages in the filtration. The middle one happens to be of rank 0 because I took 5 to be so big that 5 plus 5 was equal to 10. So there's nothing left over in the middle. The dimension of the parameter space is 15, and just hit it. And that's the end. Thank you.